Hello everyone and welcome to this talk. My name is Siavash Riahi and today I will present the paper Lower Bounds for Off-Chain Protocols Exploring the Limits of Plasma. This is a joint work with Stefan Dziembowski, Grzegorz Fabiański, Sebastian Faust and me Siavash Riahi. Stefan and Grzegorz are from University of Warsaw in Poland and Sebastian and I are from TU Darmstadt in Germany. Let's start with some motivation. We as humans need to maintain ledgers or logbooks for many different applications, such as for trading, legal agreements, or banking. Traditionally, trusted entities such as the stock market, notaries, or banks maintain these ledgers. But recent events in the past few decades have shown that these trusted entities are not really trustworthy. For example, there's a scandal regarding a company called Wirecard in the German stock market, or we all remember the 2008 housing crisis, which affected the global market and the global finance situation quite substantially. Therefore, people have been thinking, how can we force these entities to actually behave honestly as they're supposed to? Well, one can try to achieve this by using transparency or forcing these entities to be more transparent in order to detect misbehaviors early on, but others have been focusing on getting rid of these trusted entities altogether. One of the proposals to do so is using blockchains. And I must point out that there is quite a huge realistic and sometimes unrealistic hype around blockchain and blockchain technologies. And our work also tries to bring the expectations from protocols run over the blockchain to a more realistic level. But what is blockchain? Well, blockchain's core is a consensus algorithm where we have a set of parties, and as long as more than half of the parties are honest, they can agree on the latest state of the system and reach consensus. But large-scale consensus is actually expensive, and that's one of the reasons why blockchain was not able to really replace the trusted entities which I mentioned in the previous slides. For example, Bitcoin can process 10 transactions per second, while Visa payment system can process up to 50,000 transactions per second. This gap really shows that blockchain technology doesn't really scale in this case. There have been many proposals in order to improve blockchain scalability. One of the more recent ones, and the focus of this work is off-chain protocols. And by off-chain, I mean that parties only communicate with the blockchain if it is necessary, and they try to keep their communication with the blockchain to a minimum. Let me at this point give a summary of our contribution in this paper. I would like to point out that many of the terms that I will use in this slide I have not defined yet, but I will define them in the rest of this talk. We analyze a class of off-chain protocols called plasma protocols, which was introduced by Poonam Butterin in 2017. More specifically, we show that there is no perfect plasma protocol. In other words, either a plasma protocol has large exit sizes, which means that they have to communicate a lot with the blockchain, or they suffer from a phenomenon called non-uniquely attributable mass exits. And there does not exist a perfect plasma where both the exit size is small and there are no non-uniquely attributable mass exits. As I said earlier, I will define all the undefined terms in this slide later in this talk. Here is the content and overview of the talk. I by now gave an introduction and motivation. I will continue with some background on blockchain. Then I will define what plasma protocols are, and finally, I will summarize our results. First, let me try to give you a basic introduction about blockchain, which you can also usually see in the materials available online, or it is usually the way that blockchains are motivated. Blockchains can be seen and modeled as a trusted party who can do the following. One, maintain a ledger. This means that the blockchain is maintaining the latest balances of the users involved in the blockchain. Second, it can process transactions, so parties can send coins to one another. And finally, the blockchain can even run code, which are referred to as smart contracts. These codes can also have balances, and the smart contracts can distribute their balances according to the rules in their code. I would like to point out that not all blockchains support smart contracts, but many of the recent blockchains, such as Ethereum, indeed support execution of code called smart contracts over them. Furthermore, it is expensive to communicate with this trusted party, because this trusted party is modeling the blockchain that has to run the consensus algorithm, or you can think of this trusted party as a judge which needs to decide whether someone gets some amount of coin or not. So we would like to keep the communication with this blockchain or with this trusted entity to a minimum. Now that I have given you a basic overview of blockchain, I want to give you a different perspective of what blockchain. Blockchains can be seen as public timestamping logs, where one can prove that the message M was publicly available at time T. This is quite useful because then a party can actually prove that, for example, a patent was publicly available to everyone or a paper was publicly available to everyone. How would this look like? Well, let's say we have a party who has a message. He posts this message via a transaction to the blockchain, and after it is accepted by the blockchain network, it is timestamped, and everyone can actually see this message over the blockchain. But this message can be potentially long, and as we discussed before, publishing long messages might be expensive due to the scalability issues of the blockchain. So in order to tackle this, we can try to weaken the guarantees that we expect from the timestamping. So we define a weak timestamping guarantee where a party proves that he knew a message M at time T, but this message M might not have been publicly available. So for example, I can later prove that I know who would have become the latest president of the United States, but I did not really post this guess over the blockchain. Well, how would this look like? Instead of posting the message M directly to the blockchain, this party first hashes this message using a cryptographically secure hash function and then posts this hash over the blockchain. And after it is accepted by the system, by the blockchain, it is timestamped. To sum up, we have two variants of timestamping: strong version, which has better guarantees but is more expensive, and the weaker version, which has weaker guarantees but is less expensive. But even this weaker version might be too expensive if it's large number of users which should timestamp at the same time. So how can we deal with this? Well, we can introduce something or design a protocol called timestamping as a service. Assume we have 5 parties with 5 different messages, M1 to M5, and an operator. Instead of parties separately timestamping their messages, they send their messages first to the operator. The operator concatenates all these messages to a large message M, and then timestamps the hash of this M to the blockchain, and further returns M to the users. This is necessary such that parties can actually verify that their MI was indeed included in M, because this is not clear from the hash of the message M. This idea can be further optimized using Merkle trees, but due to time concerns, I will not go into the details of how it can be optimized using Merkle trees. What I just described is an example of an off-chain protocol, because parties try to minimize their interaction with the blockchain and only interact with the blockchain if necessary. Now, you might already see that there is a problem with what I just described. What if the operator is malicious and does not explain this HFM or does not return M to the users? Well, in this case, the users need to timestamp their messages themselves separately because they're not sure if their message was timestamped or not. This type of attack is called data unavailability, where the operator simply withholds some data from the users. The biggest problem with data unavailability is that it is non-uniquely attributable. What do I mean by that? Assume Alice goes to a judge and says, the operator mounted a data unavailability attack. I did not receive M from him. The judge cannot be certain if Alice is telling the truth or not, because it could very well be that the operator was honest, but Alice is lying and she indeed received M from the operator. In other words, no judge can decide who is malicious, the accuser or the accused. This would be quite problematic for plasma protocols, and I will discuss this later in the talk. Okay, now that we have seen this timestamping as a service, let us try to extend this concept and build an off-chain bank. And this off-chain bank is indeed what we refer to as plasma. Note that in the literature, plasma protocols are also called commit chain. So, the main idea behind plasma protocols is as follows. Instead of parties submitting their transaction to the blockchain, they submit their transactions to the operator, which must be digitally signed, of course. Furthermore, the operator periodically timestamps the latest state of the system, plasma system, such that the parties can refer to their balance which they had in the plasma system. More precisely, the operator maintains his own ledger L. He publishes the content of L off-chain, for example, on his own web page, and he periodically, for example, once per hour, publishes the hash of L over the blockchain. Let me continue with an example, and this would be the running example that we'll use for the rest of this talk. We have three parties, Alice, Bob, and Charlie, and the ith state of the plasma system is as follows. Alice has 5 coins, Bob has 3 coins, and Charlie has 7 coins. Now parties can make transactions. Alice can say, I want to send 1 coin to Bob. Bob can say he wants to send 3 coins to Charlie. The operator gathers these transactions and updates the state of the plasma ledger. Furthermore, as I mentioned before, the operator needs to timestamp periodically the state of the plasma ledger. Technically, these hash values are indeed stored on the plasma smart contract, such that the parties can later refer to them, right? What I just described can be extended to allow depositing and withdrawing assets directly from the blockchain to the plasma smart contract using the monetary capabilities of the blockchain. Let me try to give a high-level overview. Assume Li is the latest state of the plasma system, which means that the plasma smart contract has a balance of 15 coins because the sum of all the balance of the users here is 15. Alice submits a transaction which states that she sends 1 coin to the smart contract. This increases the balance of the smart contract to 16 and of course reduces the balance of Alice on chain by 1. In the next state of the plasma ledger, Alice's balance would be increased by 1 to 6 in order to incorporate the transaction that she just made. I left a lot of details out here due to time reasons, but if you want a more detailed explanation, I would refer you to our paper or the materials that are available online regarding plasma protocols. Furthermore, I will not explain how exiting works. The process is very similar to depositing. Here, I would like to point out that one of the features of plasma protocols is that the operator does not need to have collateral in the system. So the operator does not have to additionally put money in the system in order to guarantee security. This is in contrast to other off-chain protocols such as channels, where the operator or the intermediary indeed needs to put huge amount of collaterals in order to guarantee security. We will not go into details how channels work here. I would just like to point out this for people who are familiar with channels and plasma protocols. So, what are the main features of plasma protocols? Well, we expect that if the operator is honest, he will achieve huge on-chain savings. And that is indeed true, because the parties do not have to submit their transactions on-chain. They submit it off-chain. This is quite good. But we also expect that the malicious operator cannot really steal coins. To achieve this, parties need to solve conflicts on-chain. For example, if some data unavailability attack happens, parties need to solve this on-chain, which means that users have to monitor both the blockchain and off-chain state of the system to see if they match and everything checks out. There are quite a lot of variants of plasma protocols that have been designed. This is a picture from 2018, and some of the projects here might be abandoned already, but as you can see, people have really tried to produce specific plasma protocols for specific purposes. But all in all, we can categorize plasma into 2 main categories. 1, plasma cash, where users own tokens similar to cash. And 2, fungible plasma, also known as plasma MVP or no cash, where users have accounts similar to checking accounts. And as in real life, implementing plasma cash is easier than implementing fungible plasma. Well, we have had cash for like thousands of years, but checking accounts have been around for maybe a few centuries at most. And we will see later why this is also the case here in these 2 variants of plasma. In a bit more details, in Plasma Cache, we assign tokens to users. For example, token 1 here belongs to user 2, token 2 belongs to user 1, and a user can actually own multiple tokens. In Fungible Plasma, however, it's kind of the other way around. Users are assigned to the number of tokens they own. So, and this number can also be a real number. It doesn't have to be like a natural number. Similar to real-world cache, if a user wants to withdraw k tokens from the Plasma Cache system, he needs to withdraw them individually. So he needs to actually communicate a lot with the blockchain. This is also the same situation with cash. If I go to a bank and if I want to withdraw a lot of money in paper form, well, I might need to bring a suitcase with me. However, Fungible Plasma, similar to real checks, is more prone to cheating. And that is what we'll explain in the next slide. Fungible Plasma suffers from a phenomenon referred to as mass exits. Let's see this in an example. Assume Li is the latest state of the plasma system, but the operator turns malicious and does not really explain the new state, Li plus 1, to the users. Now, you might be wondering, okay, why is this a problem? Well, what if a malicious user who is colluding with the operator now has a balance of 15? So the balance of this user is increased to 15. Well, this user can actually drain the smart contract. He can, if this user actually exits with 15 coins, there won't be enough coins available for the rest of the users to exit. Which means honest users must exit before it is too late. This is called mass exit because parties have to exit immediately. Recall that this attack, this mass exit phenomenon, is caused by data unavailability, which is non-uniquely attributable. Now, why doesn't Plasma Cache suffer from mass exits? Well, Plasma Cache offers something called exit challenges. Assume here that we have 3 tokens assigned to Alice, Bob, and Charlie. And the operator turns malicious and says, no, token 3 actually belongs to me or another party that I know. No longer belongs to Charlie. And he withholds this latest state of the system. So we are again on the data unavailability attack. Now, if at some point this malicious user tries to exit token 3, Charlie would get mad. But Charlie can do something smart here. He can say, well, I own token 3 in Li, in state I, the ith state of the ledger, the Plasma ledger. So you're claiming that token 3 now belongs to you. Give me a proof that I transfer token 3. Since the transaction must be signed and forging Charlie's digital signature would be impossible except with some negligible probability, the adversary would fail here and can indeed be punished for trying to steal Charlie's coin. To sum up, in Plasma Cache, transferring coins require a digital signature, which means that the malicious operator cannot really steal coins. And misbehavior can easily be challenged over the blockchain. But Fungible Plasma is not like Plasma Cache. Operator can attempt to increase another user's balance. He can stop explaining the latest state of the system to the users, and users cannot easily detect what went wrong, and they cannot easily challenge it. Which brings us to the table that I showed at the beginning of the talk. Plasma Cache suffers from large exit sizes, but does not suffer from non-uniquely attributable mass exits. But Fungible Plasma, although having short exit sizes, suffers from non-uniquely attributable mass exits. Now you might be wondering, are mass exits a huge problem? Well, they indeed are, because blockchains have low throughput and cannot really handle simultaneously many exits. Therefore, exit timeouts must be large. I think in the Plasma community they usually refer to 7 days, which is quite a lot compared to other systems such as Visa or normal banking systems. Furthermore, the attack that I just described does not have any cost for the operator. The operator must simply withhold data, and the attack is not uniquely attributable, which means no one can be really punished for it. Now the main question is this separation inherent? In other words, is there a Plasma protocol with short exit sizes and no mass exits? Well, this brings us to our result. We answered this question in our work. And the answer is no. There is no perfect plasma protocol. I would refer you to our paper for the full proof and the detailed results. But in short, we show that either we have a situation like plasma cache, which requires large exits, or we have a situation like fungible plasma, which requires mass exits. Let me give the main idea behind this proof and the observation that we had. Assume now we have three parties, where Alice has 1 coin, Bob has 0 coins, and Charlie has 1 coin. Now, Alice, which means that actually the total balance of the plasma contract is 2. Now, Alice sends 1 coin to Bob, which means that the next state of the system would have Bob with 1 coin. Furthermore, the operator does not publish this state to the honest users, which is Charlie here. Bob tries to honestly exit from the system, and he should be able to do this. Everything went through honestly, and he can exit 1 coin, which means the balance of the system would be reduced by 1. Now Alice can try to revert her state to her state in Li and claim that she never transferred any coins to Bob and attempt to exit. Naturally, if Alice exits, Charlie will not be able to exit. So how can we prevent Alice from exiting here? Well, either it is clear from Bob's exit that Alice cannot exit, which means that we are in some situation like plasma cache, where Bob is exiting a token and a token cannot be exited twice, or Charlie must exit before Alice, which would mean that we will end up in a situation like fungible plasma. Now let me try to extend this idea and give more intuition behind our proof. Until now, we had only 3 parties. But what if, instead of just 3 parties, we have 2n plus 1 parties? We have n parties here, which we refer to as Camp Alice, and n party, which we refer to as Camp Charlie, and the Alice camp is chosen randomly by the operator and corrupted. And the parties in Camp Charlie are separated from the rest of the system, so they're under data and availability attack. Furthermore, the total balance in the system is 2n instead of just 2 coins. Now, the parties in Camp Alice can send all their coins to Bob. Bob can, as before, try to exit all his new coins, which would mean that the new state of the system would only include n coins. Parties in Camp Alice can also claim now that they never sent any coins to Bob. Now, in order to guarantee security, no one from Camp Alice should be allowed to exit. Therefore, the description of Camp Alice should actually be known to the smart contract. Otherwise, if even one person from Camp Alice exits, there is one person from Camp Charlie that is not able to exit anymore. Hence, the total communication with the contract must be overall large. Why? Because Camp Alice was chosen randomly, and a random subset cannot be compressed more than some certain amount, and therefore, in order to describe this set to the smart contract, the overall communication must be large. Which means that either Bob's exit was large, or people in Camp Charlie try to mass exit. Note that for technical reasons, we assume communication locality, which means that users only communicate with the operator. This is necessary, and not with each other. This is necessary in order to exclude trivial protocols where parties actually run some consensus algorithm off-chain, which is not the goal of Plasma. The goal of Plasma is to actually scale the blockchain, and running a consensus algorithm off-chain between a huge number of users is not really scalable. With this, I would like to conclude this talk. We initiate the study of lower bounds for off-chain protocols. And we show that there is an inherent separation between plasma cache and fungible plasma, which means that both plasma variants have their place and use cases. For example, if the operator is semi-trusted, then fungible plasma would be much more efficient than plasma cache. But in case the operator becomes malicious, then plasma cache might be a better choice. Now, regarding future works, well, we just initiated the study of lower bounds for off-chain protocols, so there are many things that can be worked upon and improved. For example, we only analyzed plasma protocols, but there are huge class of other off-chain protocols such as channels, channel networks, or virtual channels, which can be analyzed. Furthermore, one can improve our results by seeing whether, for example, this assumption regarding communication locality can be changed or removed, or try to change some of the modeling choices that we made and see if the same result can be achieved. With this, I would like to thank you all for your attention, and if you have any questions, feel free to contact me, any of the co-authors, or use the live panel to ask your questions. Thank you very much.